Okay, now we're going to go through the coding investigation using the Hill cipher technique. We have the letters here from A to Z. They can be represented by numbers from 1 to 26, and it's on a cycle. So 27, for example, would be the letter A, 28 would be B. It just continues going around on a cycle. Now we want to send coding, so convert letters into numbers, send them across, and it has to be decoded. So part A, we're going to code the word math. Now if we get the letter M, M corresponds to 13, so we put in the matrix, we put M first, up the top left, and then A is the number 1, top right, and then bottom left is T, which is 20, and bottom right H, which is 8. So that's math coded as a matrix in number form. We then have to code it to try and make it difficult for it to be cracked by someone. So what we do is we could add a matrix. Now the matrix we're adding is N, 2, 7, 13, 5. And when we send that across, we give that to the receiver. So the sender, to code it, has to have the math matrix, and then you add on the coding matrix. So that's this one here plus this one here. You add the corresponding elements, and that's our message we're going to send to our receiver. Now the problem with the message is that there's a number 33 outside the 26, so we have to subtract multiples of 26 to try and get it in the range, and if you subtract 26 you'll get 7, so 26 is equivalent to the number 7. Now we can read what the letters of those corresponding numbers are, and if you look up at the top and you look at 15, that corresponds to O, etc. So math gets coded as OHGM, OGM, and that gets sent through the airways to our sender, and then their job is to decode it. Now question 1, explain how the receiver would decode the message. Okay, so what they need to do is do the opposite of adding, which is taking. So they get OHGM. The first thing they need to do is express that as a matrix of numbers, and they'll read 15, 8, 7, 13 off the alphabet. And then because the sender sent them the coding matrix, which is this one, 2, 7, 13, 5, and they're told that that was added, well then they have to subtract that off. So they're going to minus 2, 7, 13, 5. Now when they do that, they're going to get the matrix 13, 1, minus 6, and 8. Now you can see we've got the original message apart from this number here, minus 6. So the original one was 20. So the receiver would see that minus 6 lies outside the alphabet, 1 to 26, so they have to add on 26, a multiple 26 to get it in. So if you add on 26 to that, then you'll actually get the original message, 13, 1, 28, and that can be read off the alphabet as math. Okay, so what you have to actually explain that in words. You have to say that the coding matrix is subtracted, and then you need to add or subtract multiples of 26 to get it into the alphabet. Okay, question 2. Using this decoding this method, you should be able to decode this. Now you do that. First thing is you have to split it into groups of 4. So ULAI, VORY, TVBU. There'll be 3 separate matrices, 2 by 2 matrices, and you want to subtract off that 2, 7, 13, 5 from all of them. to get the original message. Question 3, the message was 12 letters long, so it could be sent in groups of 4, 3 lots of 4, but if the message was not a multiple port, it says how would you send the message. For example, if there was an S on the end of this, well, one way of doing that is you could actually use 0, 0, 0. So you could have the S, and the S corresponds to 19. So your matrix could be 19, 0, 0, 0. Could be your last matrix. Because the 0 doesn't stand for A, that's the number 1. And you can think of other way of doing it if you want, but that's question 3 answered. Question 4, can the receiver apply the decoder matrix to OGM even though the sender is unaware that a multiple of 26 has been subtracted? We've already shown that up here. Can you justify your answer using algebra? So this is actually showing that it'll work for all cases. To show using algebra, we have to, instead of using math, use a general matrix A, B, C, D, and we want to code that. So to code that, we have to add on the coding matrix, which is 2, 7, 13, 5. And so that will give us our coded matrix of 2 plus A, 7 plus B, and 13 plus C, and 5 plus D. Now, one of those or more could be outside the 26, the alphabet. So we have to add or subtract multiples of 26. So sometimes we have to do this. We go plus 26 and it's a multiple of that. So in here you have MNOP, where these in here, these letters, they are whole numbers and they could be plus or minus, so that you're either adding on or taking off a multiple of 26. Now I can see that the receiver, if they decode this, what they're getting is something from here, and they have to try and get the original message here. Now, is that possible by subtracting off the coding matrix? So we'll have a go at that now. So what the receiver would do is they've actually got this matrix here, 2 plus A, 7 plus B, 13 plus C, 5 plus D, and what they're going, and also they've got the multiple matrix added on. I'll keep it as a separate matrix. You could have actually written that as 2 plus A plus 26N, 7 plus B plus 26N, and written all as one matrix, but I'll just keep it like this for simplicity at the moment. And this is what the receiver gets, and the receiver immediately subtracts off the coding matrix, which is 2, 7, 13, 5. And we can see if we do that, it doesn't matter about the order, which order you do matrices when you're adding and subtracting. So we could actually combine these two, we could subtract these two. And so you can easily see you would get 2 plus A take 2 is going to give us our A, 7 plus B take 7 is going to give us B, and we get our original message plus, and we've still got that same multiple sitting there, 26 MNOP. So clearly, if this is outside the alphabet and we add on multiples of 26, which would counteract this, we'll get our original matrix back, A, B, C, D. Now you have to put that in words rather than just put all that there in the assignment. It doesn't make sense. You have to actually logically go through that to explain how subtracting n is going to work every time, even though a multiple of 26 has been added and the sender doesn't know which 26 has been added to it or subtracted from it. Okay, so that's part A. Part B is now going a little bit further now with multiplying them. Now part B is similar, so I'll let you do that and ask me any questions individually at school if you need it answered. I'll jump to part C. This is cracking the code using reciprocal modulo arithmetic. Now we're going to look at cracking this if, for example, you knew 4 letters. So for example, a letter is always started off with the word dear. So you can imagine that if you guess that the first four letters were dear, is that enough information to crack the code? You can if you use this technique down below here. It's quite involved. First of all, we need to use some terminology. First of all, the difference between modular arithmetic and reciprocal modulo arithmetic. Modular arithmetic is just what we've already done, converting the alphabet A to Z to numbers from 1 to 26. So, for example, if you had the number 68, that's this one sitting here. So 68, that one there. 68, if you subtract 26 twice, then it's equivalent to 16. You could have done that by doing 68 divided 26, and you get 2, with a remainder of 16. So it's the remainder after you divide by 26. That's called modular arithmetic, changing a number into a number between 1 and 26. Now, reciprocal modular arithmetic is changing a number into 1. So, for example, the number 3, when you multiply by its reciprocal modulo of 9, so when you multiply these two here, it gives the number 27, which is equivalent to 1. So if you ever want to change a number into 1, these are the numbers you have to multiply to get that. Now, you just have to accept that. It's quite complicated describing why this works, but you can accept that as a rule, as the reciprocal modulo arithmetic rule. Now, we're going to use that in row operations. To crack the code, we're going to use an example of dear, so using the first 4 letters. Now let's pretend that the coded message begins with IOSB, and we have to try and guess what the coding matrix is. So down below here, what we're saying is that the IOSB, that's the received message, multiplied by, that's this dotted line, multiplied by something gives dear. Now dear is 4, 5, 1, 18 from the alphabet, and IOSB is 9, 15, 19, 2. We have to work out what this matrix is. This is a shorthand. What this is called an augmented matrix. It really stands for this: 9, 15, 19, 2, multiplied by the augmented matrix, which we're trying to work out, say A, B, C, D. They are the unknowns we're trying to find. When you multiply those two together, we get the original dear, 4, 5, 1, 18. So we're going to be working out the decoding matrix, this matrix here. This is the matrix we have to post multiply it by to get the original message, and then we can use that to decode everything in the sentence. Now to get that ABCD coded matrix, we could use the inverse. If we considered this to be matrix A, that the unknown X, and that B, we could pre-multiply by the inverse on both sides. So we have A minus 1 times AX equals A minus 1B. A minus 1 and times A is the identity. Identity times X is A minus 1B. And identity times X is X, which is what we're trying to find. Now, if you do that on the graphics calculator, if you just do the inverse of A and you multiply by B, you actually get decimal values, and you can't actually read off the alphabet what those actually represent. So what we're going to use is row operations, and we actually get this line here when you do row operations. If we can get it down to the identity times by the x equals this, then we'll have what x is. And you can see what we do is we reduce it to the identity, and that's this here, I times x, and this bit here is your a minus 1b. But we have actually found that x is actually equal to this, and x is the coding matrix A, B, C, D. Okay, so to do that, we're going to apply row operations as explained here. So the first thing to do is we have to get this to be identity. So this 9 has to become a 1. We need a 1 there. We need a 1 there, a 0 there, and a 0 there. But we have to do the multiplication and addition rules to the whole row, so we're not changing the equations or the matrices. So the first thing we do is we'll get the 9 to a 1. And now remember, to get something to a 1, we can use this reciprocal modulo technique. So if we look up here, see up here 9, we're going to multiply by the 3. So if you times 9 by 3, you'll get 27, which is equivalent to 1. If you do 15 times 3, you get 45, 4 times 3, you get 12, 5 times 3, you get 15. So this whole row here, we actually write like this: row 1 has become 3 times the old row 1. Now we have to we're going to replace the 45 by the number in the alphabet using the modulo arithmetic. So 45, if you minus 26, you'll get 19. So 45 is now 19 sitting there, and we still keep the same numbers. That's done that row. Now we come down and we try and get this 19 to be 0. To get that to be 0, we have to do the row, I'll fill it over here, row 2 becomes, we're going to get 19 times row 1, and we're going to subtract row 2. Actually, they've done it the other way when I can see the negatives, so it doesn't matter which way you do it. They've actually done row 2 minus 19 times row 1. So this is 19 take 19 times 1, so that's 0. This is 2 take 19 times 19, which is that value. This is 1 take 19 times 12, which is that. And this is 18 take 19 times 15, which is that. So we've applied that to the whole row of the augmented matrix. Now we're 1, 0. Now we have to get the 5 to be 1. And if we look up at the reciprocal modulo for 5, we can see we need to multiply 5 by 21. So this one here, the 5, when you multiply by 21, you will get the equivalent of 1. And then if you multiply 7 by 21, you'll get that. 19 times 21, you'll get that. Now we have to change these numbers into numbers in the alphabet, so we subtract multiples of 26, and so you'll get that to be 17 and 9. Now we want to get the 19 to be 0. To do that, we're going to do row 1 becomes 1 subtract 19 times row 2. And if you do that, you'll get 0 for that one. This will be 12 take 19 times 17, and this will be 15 take 19 times 9. Now we have to get those numbers to be in the alphabet, so we subtract multiples of 26, and so that comes to 1 and 0. And so finally we've got our answer 1, 0, 17, 9. So that was the coding matrix. Just to test that it works, you can grab the 9, 15, 9, the 9, 15, 19, 2, 9, 15, 19, 2. And if we multiply by this matrix, we will get our original deer, which is 4, 5, 1, 18, coming out. So this is it's really the decoding the matrix. Okay, so now what you need to do is a similar sort of thing, but you need to do it for the first 4 letters of your name. Here, the first 4 letters of your name. So using your first 4 letters of your name, you can code them using the original coding matrix, which was this one here, 2, 3, 1, 2, and then try and use that same technique, row operations, using this technique to decode it, to see if someone could decode it using that process there.